So this is session 9B, distributed systems. So this session has 3 talks. The first talk is from Athanasios Xygkis. Athanasios is a 5th-year PhD student at the Distributed Computing Laboratory of EPFL in Switzerland, working under the supervision of Professor Rachid Guerraoui. His research primarily focuses on the design and implementation of distributed algorithms and systems that leverage modern hardware to achieve microsecond-scale latency.
Thank you for the introduction. So this presentation about uBFT, it's a system that enables microsecond-scale applications tolerate arbitrary faults. There's a joint work with Marcos and Naama from VMware, my colleagues Rachid and Antoine from EPFL, as well as Igor from MIT. What our system is effectively doing is replicate at microseconds. And we consider this to be an important problem because microsecond scale computing is here. And we see that, for example, in the financial sector as well as in the industrial sector, there is need for microsecond computing. And in particular, in the data center today, we see that there are a lot of microservices like microsecond scale key value stores. And all of these are critical enough to require to be able to tolerate failures. The way we tolerate failures is via replication. And if the application itself operates at microseconds, then we need to also replicate at microseconds. Otherwise, the moment you replicate for fault tolerance, you would lose the microsecond scale characteristics. So consider this to be very important. But in the data center, what kind of failures do we really need to deal with, right? Typically, we have to deal with crash failures, meaning that applications work and then they stop working, they crash. This is a clean type of failure, but if you take a look, you see that the hardware does not behave so well these days, especially due to miniaturization. So failures go beyond crashes. We can see that we have corruption in the memory subsystem, in the hard drives. We also have corruption inside the CPU these days. And also, you can also have malicious behavior just because you can. And so we believe that to tolerate all these failures, it's important to look at Byzantine fault tolerance. The problem, though, with Byzantine fault tolerance at the microsecond scale is that it's expensive. And by that, I mean that it either requires many replicas. So typically, in a Byzantine protocol, to tolerate F machines crashing, you need to have 3F+1 replicas. But if you don't have Byzantine failures, you can get away with only 2F+1. Or, in other cases, you need to rely on heavy cryptography, which at the microsecond scale, it adds a lot of latency. So here on the right, I have a diagram where I can show what this means. To do crash fault replication, you need merely 1.5 microseconds. But the moment you need to do a signature operation, like a sign on verify, you need to spend something like 19 and 35 respectively. Overall, this is 55 microseconds, and this makes it quite expensive. So what we ask ourselves is, can I have a Byzantine solution that is as cheap as a crash fault tolerance solution? That's what we're trying to do with our system. And the answer is not, it is positive, but it's not so easy because we have a lot of conflicting requirements. So as I said, 3F+1 is expensive. And to drop down to 2F+1, we need to theoretically trust some part of the system to not behave arbitrarily. Everything can do, but a small part, our trusted computing base, has to fail only by crashing. And we put that trust in our work in disaggregated memory because it's a simple component that is also becoming mainstream. Now, the moment you go down this rabbit hole, you have some problems. Because, again, theoretically, signatures are necessary. You cannot avoid them. But because they're expensive, you need to find a way to actually hide them and take them off the critical paths to keep latency in low numbers. And an additional problem is that because your quorums on 2F+1 replicas are small, to actually prove that the replicas behave correctly, you need to keep everything that has happened. And this basically blows up memory, and that is something that a practical system cannot do. So our question now, our goal, or better, our goal is, can we actually stay at 2F+1 and deal with these problems on the left, while at the same time deliver microsecond scale performance? And we believe that we can strike this a good balance with our system uBFT, which have a high-level depiction here. So there's a client on the left, and the purpose of the client is to push some requests to the application on the right. For fault tolerance, we replicate, so we have 3 replicas. One of them is the leader that is driving the replication process. And what replicas do is they receive the request from the client, they sequence it using consensus in the middle. So they decide on the order of request, then they push that request to the application, they execute it, and then they reply back to the client. This is a fairly standard design in replication, but I would like to draw your attention to a few components that is specific to uBFT. One is disaggregated memory, that, as I said, is used to keep the number of replicas to 2f+1. The other one is unanimity, so it's a fast path that we use to lower the latency, and the way we do that is by leveraging unanimity. This means that when all replicas are timely and they do not exhibit malicious or incorrect behavior in general, then our system does not need to have signatures on its critical path. And lastly, what is fundamental about consensus in general is that you need to find a way to prevent equivocation. So to prevent, for example, the leader in this case, to send different sequence numbers to different replicas in an attempt to actually corrupt the state of the application. And the way we do that is with consistent broadcast. So now, when we combine all of this together, we actually end up having an end-to-end replication latency of approximately 9.5 microseconds, so a sub 10. So for the rest, and in the interest of time, I'm going to explain to you a little bit how consistent broadcast leverages disaggregated memory and unanimity to get its performance. And I will start with a slow path. So as I said, it prevents equivocation, so correct process cannot deliver different messages. They cannot be tricked. And in its slow path, it requires signatures. So here on the left, I have 3 processes. One is P1 that is trying to broadcast a message. There are 2 other processes, P2 and P3, that will deliver that message. And on the right, we have disaggregated memory, which has access control. This means that the top slot of that memory is only writable by P2, and everyone else can read, and respectively, the bottom slot is only writable by P3. So P1 broadcasts a message and a signature. Now, P2 gets that message, receives it, it checks the signature, it says, okay, this comes from P1. Then what it does, it writes this to the memory, and effectively it's advertising that message for everyone. And this stays there forever. And then it scans the memory to see if there's a conflicting message there. So if P1 has tried to equivocate, and if not, if it's empty or it's the same message in other slots, then it delivers. In this case, because P1 did not try to equivocate, P3 is going to do the same and it's going to deliver as well. What is important here is you cannot really delete stuff from memory, because if you delete, then you may actually not see a conflicting message, and then that's equivocation, and that's a fundamental problem that we're trying to avoid. And this is actually a problem with this abstraction consistent broadcast. That's why in our work, to avoid infinite memory, we have to modify this abstraction, and we call it consistent tail broadcast, so that we can actually delete messages. I will refer you for details into the paper, but I would like to say that even with this weaker abstraction, we actually managed to build a full system, and that's very interesting. So we actually managed to solve consensus. Now moving on to the fast path. So our goal is to eliminate signatures so that we can keep latency low, and for that we use unanimity. So again, the same example as before, 3 processes. P1 is trying to broadcast, but this time it doesn't sign anything. It just sends a message in plain text, but it uses authenticated channels so that P2 and P3 know where the message is coming from. Once P2 and P3 receive this message, what they do is actually they broadcast an acknowledgement saying, yes, I have that message, and I broadcast to everyone else so that everyone else knows that I have that message. And what the process is doing effectively at this point in time is to lock on that message and say, this is what I will try to actually deliver. And it subsequently waits for everyone to receive acknowledgement from everyone. And when that happens, the process is safe to deliver because it knows that every other correct process will have received a message, will lock on that message, and even though you may need to switch to the slow path later to help others, for instance, you will still stick to that method. So equivocation is prevented, and you don't need signatures to do that. So I will give you a quick look at the replication latency. This is end-to-end replication. These ideas of unanimity and disaggregated memory are used in other layers of our protocol. Here I only describe the consistent protocol component, but we have to use them again, and for that you can take a look at the paper. And in this quick look of latency, we have a setup of 100 gigabps InfiniBand, 3 machines connected over a single switch, and we have 3 applications. One is a dummy application that doesn't do a lot of processing, it just flips the input. The other one is a financial application. It matches sell and buy orders, so it operates at approximately 5.5 microseconds when unreplicated, the blue line on the left, the blue bar, and the other one is the Redis key value store. So when we replicate these applications with a crash fault tolerant solution, we add approximately 1.5 microseconds to their execution, and that is depicted by the orange lines. And our system adds, on top of that, approximately 8 microseconds, and overall it adds 9.5, as I said at the beginning. Now, what I would like here to point out is that in Mu, for instance, in a crash fault tolerant system, you have to trust that everything is not going to fail arbitrarily. So everything is going to fail by crashing. That's a huge assumption. You put this assumption to your entire system. Here, we only assume that for only a small component of our system, which is disaggregated memory, and in fact, you only need a very little amount of that, approximately 1 megabyte. So in conclusion, uBFT shows that actually it's cheap to do business in replication. It's not that bad in terms of latency, and as well as in terms of replicas. And you can do this with off-the-shelf component like disaggregated memory. You don't need some special hardware device like a TPM or, for example, a trusted compute or SGX, for instance. Our solution is built around a novel abstraction that we describe in detail in our paper, which is called consistent tail broadcast. And we believe that it's an important step if you want to have robust microsecond application in the data center to consider faults that go beyond crashes. We have code available online, and again, for more details, please check our paper. I would be happy to thank you, and please, if you have any question, I'll be happy to answer it.